Hello, my name is William Schwend, and I'm a PhD student in the Autonomous Vehicle Systems Laboratory at CU Boulder. Thank you for watching my presentation on my paper, A Cascaded Control Architecture for Spacecraft with Arm-Mounted Thrusters Using Reaction Torque Compensation. In recent years, the push for in-space servicing, assembly, and manufacture has exploded. We've seen very expensive missions operating well past their design life, requiring potential upgrades and refueling in order to continue operations. Additionally, we've seen with large space systems, such as the International Space Station, there's a need to assemble superstructures in space that are larger that can fit in a singular launch vehicle. Finally, as we look to take advantage of the unique environment space offers and look to extend missions beyond the local area of Earth, the need to manufacture items in space has expanded. This has all led to a significant growth in technology that can enable ISAM operations. One such technology is the use of robotic arms on spacecraft. These arms are crucial for performing many required components of ISAM operations, such as grappling and fine motor skills for assembly and manufacture. This technology having a relatively large base of controls research, which has produced a variety of coordinated controls approaches for integrated control of the spacecraft hub and its attached arms. Traditionally, these controls rely on fixed hub-mounted thruster configurations, often supplemented with momentum management devices, allowing control actuation of the spacecraft to be done independently from arm actuation. However, recent work has begun to investigate how we can shift away from these static thruster configurations to reconfigurable thruster arrays. Two such examples would be dual gimbal-mounted thruster platforms and robotic arm-mounted thrusters. Both of these solutions do introduce complexities. In particular, arm-mounted thruster configurations produce highly coupled dynamics where thruster actuation is now dependent on joint configuration. Additionally, the motion of the arm results in reaction torques acting on the spacecraft hub. These reaction torques can become significant when rapid reconfiguration is needed, such as during proximity operations, and can disturb attitude pointing unless directly compensated. The reconfigurable thruster arrays do, however, offer many advantages over fixed configurations, such as a reduction in mass by potentially requiring fewer thrusters and less support equipment to be on board the spacecraft, as well as minimizing fuel expenditure as less thrust cancellation is required to negate unwanted thruster forces produced by static configurations. To illustrate the importance of maintaining hub pointing, we look at an example proximity inspection mission, where a deputy spacecraft must inspect a chief spacecraft while following a relative motion trajectory. To accomplish this, the deputy must keep its sensor pointed at the chief in order to both meet the mission inspection objectives, but also to ensure safe operations between the two spacecraft. In this work, the deputy spacecraft is modeled using a rigid hub with robotic arms comprised of rigid links connected by 1 degree of freedom revolute joints. The thrusters are then mounted at the tips of the arms. This leads to the coupled equations of motion shown here, where the translational, rotational, and joint dynamics are coupled through the system mass matrix and the bias terms in the C vector. The key challenge is that the rapid arm motion can generate reaction torques on the hub, which can disturb the spacecraft attitude and cause sensor line of sight to drift. To address this, we introduce a prescribed hub torque term, highlighted in green, which is used to counteract the effect of arm motion on the spacecraft during arm reconfiguration. This prescribed hub torque term is embedded into the inner loop of the cascaded control architecture shown on screen. For this controller, the outer loop handles the mission level objectives, both translational and attitude, and computes the overall desired control wrench required. That wrench is then passed into an allocation block which selects the joint configuration and thruster firings that can best realize our desired control wrench. The inner loop then executes this command in two phases. First, the arms are reconfigured while the prescribed hub torque is applied in order to preserve line of sight pointing. Then the thrusters are fired to apply the commanded wrench while keeping our spacecraft rigid by not allowing our arms to move. The outer loop of the controller treats the spacecraft as a rigid body based on two assumptions. One, there is a separation of timescales between the outer and inner loops, where the inner loop is assumed to drive the joints to their commanded states before the next outer loop command is executed. And two, the joints are held fixed during thruster firing. The translational portion of the controller drives the deputy system center of mass to the desired relative position and velocity using a standard relative motion Cartesian PD tracking law with feed-forward compensation. The attitude portion of the controller computes the torque required to track the desired pointing reference. For the attitude controller, the nominal hub inertia is used as the inertia model. The true system inertia changes as the arms move and is not known a priori, as we do not yet know what our arm configuration is. The hub inertia is, however, assumed to be dominant. Thus, the inertia contributions of the arms are treated as a bounded modeling error. The classical MRP feedback control law is therefore chosen for the attitude controller because it's been shown to be robust against such modeling errors. Once the desired force and torque are computed, they are combined into an overall desired control wrench. The final step of the outer loop is the joint thruster allocation problem, which maps that desired wrench to a desired joint configuration and thruster firing by solving the nonlinear optimization problem shown on the screen. The inner control loop is responsible for executing the command generated by the outer control loop. The first phase is joint actuation, where the arms are reconfigured to their desired orientations. During this phase, the thrusters are inactive and the prescribed hub torque is used in order to enforce that zero angular acceleration of the spacecraft hub takes place. This prevents reaction torques generated by arm motion from disturbing the spacecraft pointing. The regulation-based joint controller shown here drives the joints to their desired orientations and brings them to rest at that orientation. Once the required joint motor torque is determined, the prescribed hub torque can be solved from the rotational dynamics in order to satisfy our zero hub angular acceleration constraints at every single inner loop control step. Once the arms are reconfigured, the second phase of the inner loop is thruster firing. In this phase, the prescribed hub torque is set to 0, such that the thrusters are the sole actuators producing our desired outer loop control wrench. The joint motor torques are then used solely to hold the arms fixed at their current orientations throughout the duration of thruster firing. To evaluate our proposed controller, the representative spacecraft inspection mission, shown on the right, is simulated. Over the 8-hour scenario, the deputy must track this relative trajectory while keeping the hub's first body frame axis pointed at the chief. The tracking performance of the controller is shown here for the nominal case, where the prescribed hub torque is unconstrained. The left plot shows the position error of the deputy system center of mass. Because the spacecraft starts off the desired trajectory, the initial error is relatively large, but the controller smoothly drives the error down and reaches steady state tracking after roughly 3 hours. Once converged, the position error remains on the order of approximately 1 centimeter throughout the remainder of the simulation. The attitude response converges significantly faster. The right plot shows the MRP attitude tracking error components associated with pointing, which settle within the first few minutes of the simulation. After convergence, the average pointing error is consistently around half a degree. The prescribed hub torque demand for the nominal case is shown here. The plot on the left shows the torque required over the full simulation to enforce the zero hub angular acceleration condition during arm motion. As can be observed, these demands can be quite large, particularly about the second and third body axes. However, the zoomed-in plot on the right shows the largest demands are typically very short-lived. After the initial peak, the required torque often decays to just 10 to 20% of its peak value within fractions of a second. This result motivates the next case that we're going to evaluate, where prescribed hub torque is limited, to evaluate whether line-of-sight pointing can still be maintained utilizing less actuator authority. To study the effect of limited torque authority, the prescribed hub torques are capped at 20 newton meters about each body axis, about a sixth of what we previously saw. The left plot shows that imposing this limit introduces additional chatter around the desired attitude, as expected, because large hub reaction torques are no longer being perfectly compensated as we reach actuator saturation. However, the controller is still able to track the desired pointing attitude throughout the simulation. The torque cap does degrade pointing performance, with the average pointing error increasing from that approximately half a degree to approximately 3.5 degrees. However, the histogram on the right shows that the distribution remains concentrated at low pointing errors, with over 70% of the simulation spent below 5 degrees of pointing error. After the initial pointing error is eliminated, more than 99.9% of the remaining nearly 8 hours of the simulation is spent with a pointing error below 20 degrees, which was our selected camera half angle. Therefore, despite prescribed hub torque saturation, the deputy maintains line of sight to the chief for the vast majority of the remainder of the simulation. In conclusion, this work developed a cascaded control architecture for 6 degree of freedom spacecraft proximity control using arm-mounted thrusters. The key addition is the prescribed hub torque term applied during the inner loop joint actuation phase, which directly compensates for arm-induced reaction torques and helps to preserve arm hub pointing during arm motion. The simulation results showed that ideal reaction torque cancellation can require large transient torque authority. However, even when this prescribed torque authority was limited, the controller was still able to maintain line of sight constrained pointing from the representative inspection scenario. Future work will focus on reducing the prescribed hub torque demand overall. This includes using reference profile joint tracking as opposed to the regulation-based joint motion presented in this work, as well as adding penalties into the allocation step to encourage unnecessarily large joint reconfigurations. We also plan to extend the architecture to account for flexible spacecraft arms in the future. This concludes my presentation. If you have any questions, please feel free to reach out to the emails listed on screen. We'd be more than happy to answer any questions you may have.